In this video, we are going to discuss rotational motion. Check your understanding question number 22. Question is based on the fact that a very small insect can drag a very large and heavier object as compared to itself. So let us see what is the question. So question is that the very often, language of the question is very often, we have seen an insect drag an object much larger and heavier than it. And this figure is the top view, the figure I have shown you just now, of an ant dragging a straw that is much larger and heavier than the ant. And it pulls the straw at one end, so this one, and rotating it slightly. Then it does the same action at the other end, and so on. First question is, how does this technique work? So to understand this, I have taken this diagram from the hint section. So let us see how does it work. This diagram is self-explanatory. Let me explain once again. So when ant is applying force like this, then what is going to happen? It is going to rotate about some point here. Fine. So when it is going to rotate about some point, you can very easily visualize this. Then if all these points will have a tendency to move in this direction, all these points, so friction will act opposite. And all these, this is, you can imagine, mentally you can imagine a hinge here, and it's going to rotate like this, right? So when it's going to rotate, then this point will move this way, and these points are going to move this way, right? So if all these points are going to move this way, then tendency is towards down, friction will act upward. So that is what is written now here. Very easily you can understand now. So what's happening? Some of the friction force, instead of opposing, it starts supporting the ant. So that is why it becomes easier for the ant to pull a very heavy object. Very heavy means as compared to, I'm comparing as compared to the weight of ant. Right? Okay, so now next is, in this we have to calculate there's a straw of mass m on a horizontal floor by this technique. Coefficient of friction is mu. How much force does it have to apply? Let us see. Okay, so same diagram I have used again. Now suppose ant is applying force F, this we need to find out. And this total is friction force F1, this total is friction force F2. Let us assume this distance is X, this distance is L minus X. And right now, the most important thing is, right now it is still in equilibrium. It has not yet started to rotate or translate, but it is just about to. So it is in limiting equilibrium, translation as well as rotational. So this force is just sufficient to make it, to make this straw move, right? Translate and rotate. Fine. So let us write few obvious equations. F1, friction force, will be what? Mu times mu mg. So mass of this part is lambda x into g. And F2 is equal to mu times mass of that part, which I have taken as L minus lambda here is mass per unit length times g. If I divide these two, I got F1 by F2 as x divided by L minus x, right? After that, if I do force balance, because it is still in limiting equilibrium, right? It has not yet started accelerating. So F plus F2 is F1. That also is very easy to see. So this F we need to find out, right? Keep this in mind. F is equal to F1 minus F2. Okay. So that's the second equation I'm naming. Now third is torque. Again, it is still in rotational equilibrium, but it is limiting equilibrium, but it is in equilibrium. So about this point, if you write torque of F will not come, and you get another equation in F1 and F2. Now, when you're writing torque, since it is a linear force, then we can assume that this effectively it is acting at the center. So from here, x by 2 distance, right? That's what I have written, and the effectively the point of application of F2 we can take at midpoint of this, right? So midpoint of that is L minus x divided by 2, right? So distance from this point is L minus x divided by 2 plus x. So that's what I've written. F1 by F2, you have got now another equation. Fine. So from here, you can see that F1 by F2 is this. And from this equation 3, it is this. We can just equate these two, right? That's now the next logical thing to do to find x. So let us do that. Before that, I've written one more equation. F1 plus F2 will be equal to what? What do you expect? F1 plus F2 is the total friction force, right? You can just add these and see. That is mu lambda, which is mass mu mg, right? So that's it now. After that, just this few calculation part steps. So F1 by F2, if we equate, then we get x as L by root 2. Now, after that, if you put x as L by root 2 in this equation or in the second equation, you get the ratio of F1 and F2, right? Anyway, now F1 plus F2 you know already, that's mu mg. So from this, and you know ratio also, you can calculate F1, calculate F2, and finally in this equation you can put F1 and F2. So that a few steps I have skipped, and then F1 and F2 you can, if you substitute, then you are going to get this as the answer. Mu mg root 2 minus 1, which is actually very small, mu mg, and then this is 0.4 of approximately 0.40% of mu mg, right? So that's it. That was my analysis. And since this question is based on the common observations, it is again a very, very important for JEE Advanced. This question as it is or with a slight modification can come definitely in JEE Advanced, right? So thank you for watching. Thanks a lot. Please subscribe to this channel and we'll meet again. Thank you.